Hello, this is problem 8 from the first problem set of David Tong's lecture notes. So we have this new Lagrangian here. So it's basically our old Maxwell Lagrangian plus this new term here. He uses C instead of A. I'm just going to leave it as A because whatever. So we're asked to find the equations of motion of this thing. So we can do that. So we have our Euler-Lagrange equations here. And luckily, our new term doesn't involve any derivatives of A. So this term is just going to be what we had before. So dl d sigma a tau will just be negative f sigma tau. And we have this d sigma here. And then dl d a tau is easy to do. You just get this. And so this is our equation of motion. And we can note that if we take the divergence of this, if we do d tau of all of this, we will get these two. Our equation becomes this. And this is symmetric. Our two partial derivatives are symmetric in tau and sigma because we can exchange them. And then f is antisymmetric in sigma and tau. So we can show that this is identically 0. And so we'll just be left with this term. And so that will imply that the divergence of A is 0. So moving on, if we take a look at the zeroth component of our equations of motion, we'll get this expression. Then I can sum over, so I can do this, split this sum into the time part and the spatial part. And so f00 will be 0 because f is antisymmetric. So we'll just be left with these two terms. And then I can write out my term here. So fi0 is di a0 minus ai d0. Or sorry, it's di a0 minus d0 ai. And then we'll have a minus di acting on that. So we'll get these two terms here. And then just rearranging this with everything on a0 on the left and this ai term on the right, we will get this. And this just tells us that a0 is not independent from our AIs. So, yeah. And then we want to find the Hamiltonian density for this Lagrangian density. So, to do that, we need our conjugate momenta fields. So, we'll need our pi mu will be dl d0 a mu. So it's basically just the 0th component of this expression. So we already know this. This is just negative f. So dl d0 a mu will just be negative f0 mu. And so that immediately tells us that the 0 component, so pi 0, will be negative f0 0, but f is diagonal, or it's a 0 diagonal because it's antisymmetric. So pi 0 is 0, and pi I will be negative f0i. So now that we have our conjugate momenta densities, we can write our Hamiltonian density. So again, this is supposed to be an h, a curly h of some kind. But it will just be this expression. So pi mu and a mu dot minus the Lagrangian density. And we know that pi 0 is 0, so we can just replace the sum with just the spatial part of the sum. And okay, so like in classical mechanics, when we're writing out the Hamiltonian, we need to replace the velocities or the time derivatives of our coordinates with the conjugate momentum. So we need to find an expression, so a dot I in terms of pi I. And we can do that, so we have our expression for pi I, which is negative f0 I. And just writing that out, we'll have these two terms, which can be written in this way. And so sure enough, we can write pi I in terms of a dot I. And so solving that for a dot I, we just get this, and then we want, ai dot with I lower, so that would be this. And we can just plug that in to our expression for our Hamiltonian density. So we get this. So that's all fine, but there's a problem in that our Lagrangian density, it is, it'll have these two terms, and this term, it involves all the derivatives of A. So it will contain some A dot terms, and we need to rewrite those in terms of our momentum, conjugate momentas. So in order to do that, I will, so if we just focus on, the Maxwell part of our Lagrangian density, I do, what I've done before is break this double sum. So first I can sum over mu, or break the sum over mu into the time and space parts, like this. And then in each of these two terms, I can do the same thing. I can break the sum over nu into the time and space parts. And so I'll end up with these four terms. So again, f00 is 0, and then we will have two terms that have f0i or fi0 in them. But f0i is just pi I. So we can immediately replace these things with our conjugate momenta densities. And then we still have, so this sum over the spatial part of the Lagrangian, it won't involve any time derivatives, so we can just leave that alone. So that part of the Lagrangian can be written in terms of the conjugate momenta in this way. So then it's just a matter of plugging that expression into our expression for our Hamiltonian density. So we'll have this term, and then also, which becomes, so these two terms add, so we'll get a minus 1/2 pi I, but then it's minus the Lagrangian density, so it becomes plus here. And similarly, plus this term. And then we can't forget about our, the Lagrangian density also contains this term, our extra term. So our Hamiltonian density becomes this. And then we can just notice that expanding this out, so this second term here will be pi I, it'll be minus pi I. So we can, and so then we'll add 1/2 pi I, so that will give us a net minus 1/2 pi I. And then the first term will just be pi I di a0. And so we'll just be left with this. So, that's our Hamiltonian density, and it is written entirely in terms of a0 and ai and our conjugate momenta densities.